Okay. Okay, so here's a game. So I deal two cards from a standard deck face down. You get to pick one. And then we flip it over. If it is an even number, like 2, 4, 6, 8, or 10, you win. Otherwise, you lose. Okay. Okay, not the most interesting game. Okay, let's start. So what I'm going to do is maybe part A of this question could say, draw a tree diagram representing the number of even cards. So representing the number of even cards that are dealt. And the event that you win. Okay. Okay, so what I'm trying to kind of say in this question is basically at the beginning of the game, before anything happens, we don't have any information, right? When I deal the cards, there's either going to be this kind of represents the number of even cards dealt. You've got three options. It could be 0, it could be 1, or it could be 2. Okay, we're going to need to put some numbers on these branches as well, but that's kind of complicated, so let's not do that right now. So if there's one out of the two cards, if one of them is even, then there's kind of two possibilities. You can either win if you pick the right one, or you can lose. However, if I deal you two cards and none of them are even, you don't really have much of a chance, right? Because you can't win. So if among the cards dealt, if none of them are even, you lose automatically, basically. Doesn't matter which one you're going to pick. And then if there are two even cards, then you're going to win, right? Okay. Is it clear? So this is like part of the tree diagram, but I haven't labeled the different branches, right? Some of these branches are pretty easy to label, though. So, for example, this one, you know, if there's 0, like this is a 100% lose situation, right? This is a 100% win situation if there's two even cards. What should I label these two branches? Yeah, 50%. So if you're in a situation where there's one even card, you've now got half of the time you're going to win, half the time you're going to lose, right? Assuming you're not like psychic and you know which one's correct, right? Okay, so it all comes down in this, to the hard part being determining how to label these three branches. So this comes back to our probability and counting stuff. Okay. So this is maybe a little bit of a review now of how to how to count these things. So there's always for these types of questions, you could think of it as an ordered selection in this case, or you can think of it as an unordered selection. Probably the most natural thing here, because like when you pick two cards and you're trying to figure out the event that neither of them are even, well, that event doesn't really depend on what order you pick the cards, right? If I pick an ace first and a king second, it doesn't really make a difference if I would have picked that king first and the ace second. So that kind of tells you that you can treat this one as an unordered selection if you want. You could also treat it as an ordered selection. It doesn't really matter. Like if this event was saying, what's the probability that the first card dealt is not even or something, that would now depend on the order. But this one doesn't really depend on the order, so my denominator is just going to be 52 choose 2. That's the number of ways to pick two cards if you don't care which order you pick them. The top should be the number of ways to pick two cards that are not even. So so the denominations that are even, there's 5 of them. There are 13 denominations in total, so there are 8 denominations that are not even, right? And each denomination has 4 cards of that type, so you've got 32 non-even cards. So can anyone see what I want to put on the numerator? Yeah. Yeah, exactly. Right, so the bottom is the total number of ways that this experiment can happen if we don't care what happens. Like, we're going to pick 2 cards. There's 52 choose 2 ways to do that. And the top is counting the number of ways that you can do that experiment that gives you this outcome, right? 0 even cards. So you pick 2 from the non-even cards, of which there are 32 of them. Okay, probability that there's 1 even. Okay, so that tells us that this branch gets 32 choose 2 over 52 choose 2. The denominator is pretty easy. It's the same thing as always. The numerator is going to be the number of ways to pick 1 even card and 1 non-even card. So does anyone see what that should be? Yeah. Yep. And let me just be kind of almost silly about this and write 20 choose 1, but like it is just 20. Like that's the correct. But just another way of thinking of it is it's like, how many ways can I pick one even card? 20 choose 1, because there's 20 even cards, which is 5 times 4. how many ways to pick a non-even card? It's this many, and yeah. Okay. So that should go on this branch. Probability of 2 evens now is going to be quite similar to this one, right? 20 choose 2, or 52 choose 2. Okay. So this would be the correct tree diagram. Okay, let's do another part. So this, so far it didn't use anything about Bayes' theorem. We just drew a tree diagram. Now we're gonna compute a conditional probability. So suppose you lose. Suppose we play the game and you lose, right? Given this, like given that we already know that you lost, what's the probability that basically you had no chance of winning? So like given that you lost, what's the probability that there were actually no even cards, so you didn't have any chance? So what is the probability Okay. So what we're trying to compute here is the probability that there are no evens, given that that you lost, right? So notice that like if this probability was turned around the other way, like if it was probability you lost, given that there are no evens, right? That would be super, super easy because we just say, oh, it's 1, right? It's in my tree diagram. It's just sitting right there, so I would just say it's 1. And also, it's also kind of obvious that like if there are no evens, you lose 100% of the time, right? But the fact that this is kind of backwards is what makes it difficult, right? You're trying to figure out the probability of this given that you lost, but there's different ways you can lose. And so like you cannot just figure this out from like immediately writing down a number. Okay? So this is where we want to use Bayes' theorem. If basically, you know, you've got something where it's you can't just compute it from the tree diagram directly. So we just write out our formula. It's the probability that there are no evens times probability you lose given that there are no evens divided by the same thing. So I can see I'm going to run out of space here. Okay, we'll write it on 2 lines. Probability no evens times probability you lose given no evens, okay, plus probability that there's 1 even, probability you lose given that there's 1 even. So you just go through kind of all the 3 possibilities here. Probability that there's 2 evens times probability you lose given there's 2 evens. Okay, so this is all on the denominator. Yeah. You're right. I'm just writing it just for like completeness here, but you can see that this part's going to give you 0. It's going to be 0 times something. So you're right, it will be 0. Yeah. But I'm only writing that just to say, okay, if you were in a different situation, you know, where there was some chance of losing here, then you'd have to write everything. But, yeah. Okay, so probability no evens. Now we just literally, I mean, the hard part is just setting this up. And then we just read stuff right off the diagram, right? So 32 choose 2 over 52 choose 2 times 1. The 1 comes from here. 32 choose 2, 52 choose 2, again times 1, plus 20 choose 1, 32 choose 1, or 52 choose 2 times a half, plus 20 choose 2 over 52 choose 2. And this is where, as you mentioned, it's times 0, because there's, I mean, I could have written something more on this tree, right? I could have said, okay, the probability of losing is 0, right? Which somehow turns out to be 31 over 51, which is about 0.60784. Okay. So basically, if you lose this game, then 60% of the time, roughly, the reason you lost was because you didn't even have a chance to win. Okay, any questions about that? Okay, so let's move on to chapter 7. I should say we're not doing all of chapter 7. In fact, we're not even doing all of for each section of chapter 7, we're not necessarily doing all of it. So today I'm going to talk a bit about 7.2. Specifically, I'm going to talk about random variables. And probability distributions. Okay, and so ignore, so if you go and look at the textbook, ignore everything in 7.2 that comes before the section on like random variables. Okay, so you'll see, like if you go through the section, you'll see some big, bold, so it's written in big, bold letters in the textbook. You'll see actually there's quite a lot of stuff we're skipping, and then the stuff on random variables is important. It kind of makes it difficult when you're going through your study guide. I understand that there's going to be a lot of questions that aren't really relevant, but yeah. Yeah, so yeah, the questions for the quiz will only be on that part of the section. Yeah. Yeah, I double checked that last night actually. Okay. So a random variable is a variable whose value depends on some kind of random experiment. Or I should maybe say the outcome of some kind of experiment, right? Actually, we've kind of implicitly been dealing with random variables for a long time, but we haven't used this word for them. I mean, even in this example, when I deal 2 cards, if I say let x be equal to the number of evens in those 2 cards, right, then x would be a random variable. It's a number which is 0, 1, or 2, and it depends on the outcome of the experiment. Okay, so let me give you an even simpler example. Flip 3 coins. And let x be the number of heads that you get. Right, so this is it's some kind of a variable, it's some kind of a number, but the value of x depends on the random event. Like x by itself doesn't have any like explicit value to it until you do the experiment, and then the value gets assigned, right? Okay, so let's kind of analyze this specific random variable a little bit. So I'm going to write a sort of chart here with all the different outcomes and what the various x values are. So maybe this is kind of clear, but so those are your 8 different outcomes, I think. Okay, so for this outcome, for example, there are no heads. So x is equal to 0. And basically, for every possible outcome, if I get that outcome, then that's the value of x is determined by it, right? So I see 1 head here, I see 2 here, 1 here, 2, 2, and 3. Okay, so we can write things like, what is the probability that x is equal to 0? Any feeling what it should be in this case? Yeah. Yep. Right, because all of these outcomes are equally likely, right? Every outcome happens with probability 1/8. And only one of those outcomes has x equals 0. Yep. Yeah, that's a good question. I mean, the thing is, if I kind of group these, like if I say that, I kind of group these all together as the event that you get 1 head or something, and I say that would give you the wrong probability in some sense. Like you'd be saying the probability of getting, the thing is the probability of getting no heads is different than the probability of getting 1 head. if I kind of group these all together and say that's one outcome that's equally likely to this one, it would be ignoring the fact that, yeah, there are 3 ways that this can happen, but only one way this can happen. Like there are 3 ways to get one head, but there's only one way to get, because it could be the first, the second, or the third, there's only one way to get this. So it is more likely to get one head than 0. I'm not sure that answers your question at all, though. But any other questions? Okay, so, right, so you've got, the thing is, yeah, these are, okay, I'm kind of thinking of this as I'm flipping 3 coins at the same time, but that's the same thing as, I guess one way to think of this is flipping 3 coins at the same time. Kind of is the same thing as flipping 1 coin, and then flipping another coin, and then flipping another coin at 3 different times. It doesn't really make a difference, I mean, whether they land at the same time or not. And if I flip them in order, you can see that, like, knowing it was heads, tails, tails is different than knowing it was tails, tails, heads, if I was really revealing them one at a time. So yeah, those are different outcomes. Okay, so if, for example, I was doing the probability x equals 1, basically, again, all these things are equally likely. There are 3 of them that have that value for x. So you should get like 3 over 8. Similarly, probability x is 2 is 3 over 8. And the probability x is 3 is 1 over 8. Right? And like, as you would expect, these things, when you add them all up, they sum to 1, right? So note here, so when I've got a random variable, if I write like this, you know, this is an event. Right, so this is kind of well defined when I write this. Like, remember, probability was only defined for events, right? You have to take the probability of an event, but this really is an event. Like, this is a thing which you can observe from the experiment. It has some probability of happening. Okay, so now let me introduce something called a probability distribution. So the probability distribution of a random variable x. Now, there's not a really good way of describing this. I'll just say that it gives the, the probabilities associated to all possible values that x can have. Okay. The reason I'm putting this word gives in quotes here is that there are different ways you can give that information, and we're going to see multiple different ways of doing it. One natural way is, like, for example, the probability distribution can be written in a table. So that's what we're going to focus on first. But it could be given by a function. So as a function, etc. But don't worry about this yet. This is coming later. So for today, we're going to kind of think of this in terms of a table. Okay, so for this experiment where we flip 3 coins, the probability distribution would look like this. So I'm going to draw like a little x here. And here I'm going to write the probability that big X is equal to little x. Okay? And then we go through, on this side, we just go through all the possible values for the experiment. So X could be 0, it could be 1, it could be 2, or it could be 3. And over here, we just write down, 1 over 8, 3 over 8, 3 over 8, and 1 over 8. Okay, so when you're asked, so this is the probability distribution. And I'll say as a table. Okay, and for now, that's the way we're going to always write the probability distribution. All right, so let's do another example. So let's say a bag contains 5 black cubes and 7 red cubes. Pick 3 at random. And without replacement, let X be equal to the number of red cubes selected. Okay, and now we want to write the probability distribution of X. Okay. Okay, so this is, I mean, basically, so there's nothing super new here, right? But, okay, we've got to practice our probability stuff. Okay, so what are the possible values for X? That's the first thing, right? We need to know what to write in this column. Sorry, what? Yeah, kind of the same as with the heads and tails thing. Right. Okay. Maybe I'll give myself more space. Okay, let's practice our probability. what's the probability that x is equal to 0? Yeah? That's the hard part of it. And then we want to put like a 12 choose 3 on the bottom. Yeah. But getting the 5 choose 3 is the tricky part. Right, because again, you know, the reason I'm doing this is an unordered selection. So unordered selection means I'm writing a choose function, not like a permutation thing. The reason I'm doing this as an unordered selection is, again, because it doesn't really matter what order I pick my cubes or anything like that. If I'm just saying, what's the probability of having no red ones? It doesn't matter if I pick which order I pick those black ones. So yeah, 5 choose 3 is the number of ways to pick 3 blacks. 12 choose 3 is the number of ways to pick 3 cubes from the whole sample, right? Okay, anyone want to do the next one? Well, let's see if somebody else has an idea for it. Yeah? Yeah, no, it's all good, yeah. It's, yeah, so exactly. You want to pick one of the red ones, 7 choose 1 ways to do that. Pick 2 of the black ones, 5 choose 2 ways to do that, and then same denominator. Everything's going to have the same denominator. Right, and then now the numbers just switch, how many you're choosing of each. So you're choosing 2 red ones, 1 black one. Right, and then here we're just choosing 3 red ones. Right. If you want to compute these numbers, this is like 1 over 22. This is 7 over 22. 21 over 44. It doesn't really matter, but 7 over 44. And in these things, if you ever want to kind of check your answer, like if you're not confident that you've got the right numbers, one thing you can do to be a little bit more confident is, like, if you add these up, you'll see that they do sum to 1. Doesn't mean you're definitely correct, but it does mean, like, if they don't sum to 1, then you're definitely not correct, right? Because the probabilities have to sum to 1. Okay. Any questions about that? Okay. Okay, so here's a question that's similar to one that comes up a lot in the study guide. So a basketball player is shooting free throws okay, and the way it's going to work is they're going to shoot one. If they miss, they don't get another shot. So, and if they score, then they get 1 point and they get another shot. And the second one, if they score, they get a point again, but then it stops. So, so if they score the first, they get 1 point and the opportunity to shoot a second. Which is also worth 1 point. Okay, and if they miss the first, then it's over, right? So let x be equal to the number of points scored Okay. Oh, and let's say that they, uh, they score with probability 0.75 on every shot. So this, yeah. Okay. Is the question clear, or? Oh, maximum is 2. So even if they score twice, that's the end of it, Or if they score once, miss once, that's also the end of it. Okay, and let's say we want to draw a probability distribution for this. So the first thing to ask yourself always is, like, what are the possibilities here? What are the possibilities for x? Yeah. Yeah, exactly. So, and this question you asked is relevant for that, right? So it's, so this doesn't keep going forever. What's the probability they score 0 points? Yeah. Yeah. Right, because you got to think about this. It's not, scoring 0 points doesn't mean that they missed 2 shots, right? Because if they miss the first one only, right, they don't get to take a second shot. So actually the probability that x equals 0 is just equal to the probability they missed the first time, right? They don't get another shot. So this is the event that x equals 0 is the same as the event they missed the first shot. What about the probability of getting 1 point? Yeah. Yeah, yeah. So, right, because, how can you get 1 point? There's only one way to do it. You got to score, but then you got to miss. Right? And now the probability of getting 2 points, well, you've got to score twice, right? And that would be the end of it, right? This is the whole distribution of this random variable x. So one thing to note about this is that in this course, we only deal with so-called finite random variables. So you've only got finitely many outcomes, right? So finitely many possible outcomes. Okay. If you take some kind of statistics courses, you will see more like kind of infinite random variables, right? But you don't necessarily need to deal with that in this course. Actually, this kind of connects to the question that was asked about this basketball thing. So suppose instead of stopping it after 2 shots, you just say, okay, basketball player, if you you keep getting points as long as you keep making the shot, you get to shoot again, right? If you score 10 times in a row, you get to shoot an 11th shot, and so on and so forth. So that would be an example of an infinite random variable, right? Because, okay, even though the probability of that person scoring 1,000,000 times in a row is pretty small, it's not 0, right? So for any number of shots, there's a non-zero probability that he would hit that many in a row. So that would be an example of an infinite random variable, right? But we don't need to really worry about that in this course.